Welcome student, PCH 4802 Unit 4. We are going to discuss in today's lecture the synthesis of saturated heterocyclic compound using retrosynthetic analysis. I am Dr. Devangar Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. The synthesis of saturated heterocyclic compound, we need to begin with cyclization. But before we start cyclization, we need to study intermolecular cyclization in making heterocyclic compound. But before that, we are going to give you here the example of intramolecular, or we can say a bimolecular reaction. Here you can see that in this reaction the product 75 act as nucleophile and will act with a similar rate with 74 as does with methylamine. So you can see that it's going to treat it with methylamine similar way. This compound 75 will treat it with this 74, and it's going to give you this dimer. And as a result of that, this is the perfect example of a bimolecular or intramolecular reaction. Now let us begin with the intramolecular cyclization reaction. Here are the example of unimolecular cyclization reaction. These are all the example of intramolecular cyclization reaction as well. So either you can say it is an intramolecular cyclization reaction or a unimolecular cyclization reaction as well. And here you can see that from member 3, 4, 5, 6, 7, we can synthesize a seven-membered heterocyclic compound using this intramolecular or unimolecular cyclization reaction. But when you go through this reaction, you come to know all cyclization are not favorable. A general cyclic amine synthesis showed that there is a large difference in rates of the formation of rings of different sizes. A five-membered rings are formed fastest, then the six-membered and the three-membered rings, while four-membered rings are formed very slowly and seven-membered rings are quite slowly. So there is different rate of formation of this different type of ring. Three and four member rings are unstable because of the strain, angular strain. You might have studied Baer strain theory. So that angular strain would be there, as you know that in a planar structure of this ring structure of heterocyclic compound, carbon is having sp3 hybridized. In sp3 generally the bond angle would be 10 for 109.24 angstrom, 105.24 angstrom. But instead that we're going to get a different bond angle that is even less than 100, and as a result of that the strain is generated in this kind of compound. The angles between the bonds are significantly less compared to 109. Sorry, in sp3 hybridized this compound bond angle should be 109.24 degree. Instead that the angles between the bonds are significantly less than the tetrahedral angle of 109.24 angstrom, and as a result the strain generated in 3 and 4 membered cyclic compound, and hence the rate of synthesis of this 3 and 4 membered ring synthesis is comparatively less than 5 membered or 6 membered ring. So the 5, 6 and 7 membered rings are unstrained, as you know that the bigger member in the heterocyclic compound of this saturated ring structure, more the number of carbon, higher would be the bond angle closer to the tetrahedral, that is 109.24 degree. But as a result of that the strain get reduced. So 5, 6 and 7 membered rings are unstrained and stable. 6 membered rings are most stable because they can have a chair conformer as well. So we have already studied the boat and chair conformer, which is in which chair conformer is more stable. Hence 6 membered ring is most favorable in synthesis of this unimolecular cyclization process compared to 3 membered and 4 membered heterocyclic ring compound. Now, when we see the further example of this cyclization, we can include one example of cyclization of 1 bromo 2 amino uh, uh, ethane to give three-membered ring in three-membered ring structure of heterocyclic compound, and this reaction is favorable because the favored conformation is right for the cyclization, and the nucleophilic nitrogen is closer to electrophilic carbon. In the terminal end, you can see the nitrogen is there with lone pair electron act as nucleophilic nitrogen, and it is closer in this three-membered structure of, we can say, 1 bromo 2 amino ethane. Nitrogen is closer than the carbon, electrophilic carbon, that is carbon number 2, and hence the cyclization is little bit favorable in this formation of three-membered heterocyclic compound. The cyclization to give the four-membered, the next example, that is of structure 11 over here, cyclization of this four-membered ring is unfavorable because the favored conformation cannot cyclize, and the another conformation that can cyclize has eclipse bond, and so the stereo arrangement is little difference that increase the distance between the nucleophilic nitrogen and electrophilic carbon. Hence the synthesis of structure 11 here, that is of four-membered heterocyclic compound, is a little unfavorable. So here there is a comparison between structure 8 and structure 11, where structure 8, that is a three-membered heterocyclic compound, which is favorable as the nucleophilic nitrogen is closer to the electrophilic carbon, while the structure 11, which is four-membered heterocyclic compound, where nucleophilic nitrogen and electrophilic carbon has a larger distance due to the stereo arrangement, the four-membered cyclic compound is unfavorable, as the favored conformation cannot cyclize and another conformation that can cyclize have eclipse bond. So the stereochemistry is the resistance or become unfavorable for the synthesis of four-membered heterocyclic compound. Both three and four-membered rings formation are unfavorable because the product when we are going to obtain and the transition state are strained, because here the carbon atom is also sp3 hybridized carbon, where we are expecting bond angle 109.5 degree, but due to this cyclized structure of structure 8 and 11, the bond angle get reduced. Hence we are not going to get a proper cyclic arrangement, and the bond angle instead of 1095 degree, it reduce, and which going to give rise to the strain. So the process in synthesis of structure 8 is little bit easier, but after the reaction completion, when you are going to get the final product, that is structure 8, then it is going to be little bit difficult to get the stable structure of structure 8, as this strain is there. Similarly, it is applicable for structure 11 as well. Now in the example, you can see the five-membered ring structure, that is structure 12A, and then it has some resonating arrangement. We're going to get the structure 14 as a final structure, that is a Chad conformer. So five-membered ring formation is very favorable as the conformation needed reasonable, and the transition state and the product are unstrained, and due to this less strain, we're going to get a stable conformer. So this is what we can discuss about the different synthesis of cyclic saturated heterocyclic compound. Next, we need to discuss the factors affecting cyclization. In this factors affecting cyclization, the kinetic and the thermodynamic factors affect cyclization to different extent depending upon the ring size and the reaction. You can see here a ring size is given ring size 3, three-membered ring size, that is very favorable kinetically, but thermodynamically unfavorable as there is angular strain in the structure. Similarly, ring size 4, that is four-membered heterocyclic compound, kinetically unfavorable as well as thermodynamically unfavorable as the strain is there. ring size 5-membered heterocyclic compound is kinetically favorable as well as thermodynamically favorable, as there is less strain, or we can say there is no angular strain. Ring size 6, that is 6-membered heterocyclic compound, moderately favorable and kinetically moderately favorable, but thermodynamically it is very favorable, while the ring size that is of heterocyclic compound 7-membered, moderately favorable kinetically, while thermodynamically it is moderately favorable as well. So the thermodynamic factors can be divided into the two part, that is enthalpic and entropic. So we're going to take with an example these two factors, enthalpic factor, thermodynamic factor, and entropic thermodynamic factor, which can affect the stability of this saturated heterocyclic compound. Now, in factors affecting cyclization, we need to discuss thermodynamic factors. In thermodynamic factors, as already discussed earlier in the previous slide, that can be divided into enthalpic and entropic components. That means enthalpic factor and entropic factor. The example given over here, that is the formation of a 5 and 6-membered ring of lectons, 5-membered lectons and 6-membered lectons are there. You can see the enthalpy value is given over here, entropic value is given over here as well, and we need to compare both the enthalpic and entropic value over here. In a chloroethanol in the other example of chloroethanol cyclize as oxyanion for uh, kinetically favored cyclization, specific base is needed. A strong base to remove the proton of a hydroxyl group completely, that is required. By contrast, the 4-chlorobutanol cyclized by general base catalysis, the proton is removed during the cyclization through weak base. You can see in the example B stands for base, that weak base is required here. Thus the three-membered rings can easily be made, but tend to decompose under the condition of their formation. 4-membered rings are difficult to make, and 5 and 6-membered rings, here you can see are the example given, that 5 and 6-membered rings can easily be formed, while the 7-membered rings can be formed whenever it is needed. Now let's begin with the example of three-membered ring synthesis. In three-membered ring synthesis, let us discuss uh, the three-membered ring can easily be made by cyclization of chloroalcohols and cyclization in base. The nitrogen heterocycles aziridines can be made by displacement of an alcohol by an amine after the activation. Here we are going to discuss the synthesis of anti-tumor and antibiotic compound. The active region of the anti-tumor and antibiotic compound here is the aziridine, that is the three-membered cyclic compound. You can see in the product 30 the three-membered cyclic compound with NH, that is the aziridine. This aziridine compound is having the anti-tumor or antibiotic activity uh, in the entire compound. JP Michael and group opened the cyclic sulfite with the azide ion. Reaction occurred at the allyl position and with inversion. Activation of alcohol as a mesylate gave 90% yield, and reduction of the azide to amine was followed by base catalyzed cyclization, again with the inversion. We're going to get 60% yield of the target molecule, and the aziridine region here you can found that is responsible for this anti-tumor antibiotic activity of the compound. Now, next example for the synthesis of three-membered heterocyclic compound, we have synthesis of aziridines and oxirans. The synthesis of aziridines already we have discussed in the previous compound, where anti-tumor antibiotic activity is given by aziridine. Here aziridines are a reactive substrate in a ring opening reaction with many nucleophiles due to the strain in their ring. We're going to study the retrosynthetic analysis of this aziridine. The disconnection approach shows that aziridine, here's the structure 14, is formed by 1,2 amino alcohols, that is structure 15. So here is the example. You can see here structure 14 is the target molecule, that is aziridine. We'll put a wiggly line over there and incline arrow shows structure 15. So structure 15 is our synthetic equivalent for the starting material. Let's study the synthesis after this retrosynthetic analysis. Step 1, the hydroxy group of beta amino alcohol, that is structure 15, is converted to a good living group, that is structure 16. Step 2, the compound 16 lost a proton in the presence of base sodium hydroxide to give the intermediate 17. Step 3, the lone pair of amine, that is 17, attacks the alpha carbon, eliminating the leaving group and the formation of 2-phenyl aziridine, that is structure 14, as a target molecule we can obtain. We can show this synthesis in our next slide. So here is the synthesis of aziridine, that is structure 14. For that we have taken this starting material and that is treated with this tosyl chloride compound. We're going to get this intermediate, and from that we can get the cyclization will take place and we're going to get this 3-membered cyclic compound aziridine. Now next, in the example of 3-membered cyclic saturated compound is a synthesis of substituted oxirants. Oxirants are an important industrial chemicals and are starting materials for the production of various important chemicals and household products in the industry. Let's begin the retrosynthetic analysis of that one. Applying disconnection approach to oxirant, that is structure 18, shows the involvement of a reagent equivalent to nucleophilic carbene, which is a sulfur ylide that is carrying positive and negative both charges on the same compound. This react with the ketone, that is structure 19, or aldehyde to give oxirant, that is structure 18 again. So this is the retrosynthetic analysis for substituted oxirant. After the retrosynthetic analysis, synthesis of substituted oxirane is given. The synthesis of oxirane, that is structure 18, can be achieved in a 3 steps, starting from dimethyl sulfide, that is structure 21. In 3 steps, you can see in this figure that step 1 include the dimethyl sulfide, that is 21, on reaction with methyl iodide forms trimethyl sulfonium ion. In step 2, trimethyl sulfonium ion, that is structure 22, is converted to dimethyl sulfonium methylide, that is structure 20, in presence of any base. Then in step 3, the dimethyl sulfonium methylide, that is structure 20, react with a ketone by a net methylene transfer to form disubstituted oxirane, that is structure 18. Now here the 4-membered heterocyclic compounds, in which we are going to discuss the retrosynthetic analysis of Jones analgesic and antidepressant tazarotene. This compound contains a 4-membered cyclic amine as an azitidine. Simple disconnection of carbon nitrogen bond in this 4-membered ring. You can see wiggly line is shown there. Give the enone. The aldol product from cyclohexanone and benzaldehyde is going to be obtained as the synthetic equivalent. Here the strategy we're going to apply for the synthesis of Jones analgesic and antidepressant tazarotene is little bit different than the retrosynthetic analysis. Whatever we are going to get the synthetic equivalent, that is benzaldehyde or cyclohexanone. Instead that we are going to use here the structure 33 rather we are going to use. It was better to use the diketone, that is 36, instead of aldehyde or cyclohexanone. So structure 36 diketone we are going to use here, made by acyclization of the morphelin anamine, that is structure 35 of 34, and reductive amination of with 3 amino propanol to give structure 37, that is dehydrated in acidic to the amine, that is structure 38. uh, Mitsunobu like treatment is given to this with triphenyl phosphine dibromo derivative converts the hydroxyl group to bromo, uh, whereupon cyclization of 32, uh, if we will going to take X as bromine, then it will going to give our target molecule, that is structure 31, that is tazadolene, an antidepressant agent. Another strategy where we can start with the other of even more surprising alternative reaction is obtained, in which the reductive amination with benzyl amine with reduction of the other ketone and cleavage of n-benzyl bond followed by dehydration gives the simple amine, that is structure 40. Now reaction with 1,3-dibromo propane gives the target molecule 31, and that way the other strategy is little short strategy compared to the first one. More example in four member ring structure, that is the synthesis of 2-methoxy 3,3-dimethyl 2-phenyl oxytane. The retrosynthetic analysis is given over here. You can see in the reactions that target molecule is 29. That is the disconnection approach will shows the 2-methyl 3,3-dimethyl 2-phenyl oxytane, that is structure 29, that is our target molecule, is synthesized from 3 hydroxy 2,2-dimethyl 1 phenyl propane 1 all, that is 1 that is structure 30, which on further disconnection shows that 2-methyl 1 phenyl propane 1 31 and the formaldehyde 32 are the starting reactants or synthetic equivalent for the synthesis of the target molecule 29. Now, after the retrosynthetic analysis, let's see the synthesis of 2-methoxy 3,3-dimethyl 2-phenyl oxetane, that is structure 29, can be achieved in a 3-step. We can see in the figure 14 below in the next slide. But step 1, which include the 2-methyl 1-phenyl propane 1 that is structure 31 and formaldehyde 32 undergo Kinezaro reaction to give 3 hydroxy 2,2-dimethyl 1-phenyl propane 1 step 2 includes to make the conditions for cyclization favorable. Hydroxyl group in structure 30 is converted into beta leaving group by reacting with tosyl chloride in presence of pyridine. And step 3, in which methoxide ion attack carbonyl group of structure 33, creating a negative charge on oxygen, which attack carbon containing the living group of tosyl living group or TS, that is tosyl oxide. Well, this is the synthesis where structure 31, 32 treated with each other in presence of potassium carbonate will give structure 30, which further reacted in presence of tosyl chloride and pyridine will going to get this tosyl derivative, which further treated with methoxy will give us target molecule. Another example of four-membered ring structure is a synthesis of cis-fused oxytocin. The anti-cancer compound Taxol also contain this cis-fused oxytocin. The cyclization of syn monotosylate in a base gives perfectly arranged nucleophile and electrophile for this cyclization, and we're going to get a high yield, that is 80% yield of this cis fused oxytocin. Next comes the five-membered ring synthesis in a saturated heterocyclic compound. They are the most favorable of all these five-membered ring compounds, and procedures such as the hydroxy acid, you can see, uh, cannot usually be isolated through the carboxylate state. Salts are stable. The only important thing is to get the oxidation level of the precursors right. Using cyclic amine, we can give here the example: a fully saturated ring, that is structure 45, would come from an alkylation reaction of structure 46. So very simple. We have a leaving group X, and it going to gives us our uh, target starting material. So if we have a very good leaving group, we're going to get this compound formed quite easily. Now here imines, that is 47, or enamines, that is structure 49, would come from aldehyde or ketone, that is structure 48. Uh, Another example you can see here, that is lactams, that is structure 50, can come from acid derivatives, that is structure 51. And compounds such as amino esters, that is structure 53, are not stable as the free amine, but are usually isolated as salts such as the hydrochloride, that is structure 52 here. When treated with base, structure 52 gives the free amines, that is 53, which promptly cyclize to lactam, that is structure 50. So that way we can get the lactane. Now another example is the example of structure 54. We can see here the retrosynthetic analysis of the sulfur containing heterocycles. The unsaturated ring, that is structure 54, does have a double bond, but it is not next to the heteroatom, and as a result of that it is an allylic rather than a vinylic sulfide. So two disconnections at the alcohol oxidation level suggest the doubly allylic starting material, that is structure 55. As it happens, we can make the diol, that is structure 56, and using that we can simply have to turn the hydroxyl group into leaving group, and the cyclization with sodium sulfide gives this heterocyclic compound, that is structure 54, and the yield would be 38%. Well, other example of five-membered heterocyclic compound include the synthesis of pyrrolidine and pyrrolizidine. Uh, Here you can see the synthesis of pyrrolidine is given, where you can see the design and synthesis of pyrrolidine. One is explained using the retrosynthetic analysis, where you can see structure 1, where 2 weekly line is applied after the amine, secondary amine group. The inclined arrow indicates that the disconnection of carbon nitrogen disconnection is carried out. We're going to get the synthetic equivalent as 1 for dibromobutane and ammonia. Here the synthesis of pyrrolidine is given. The synthesis of pyrrolidine, that is structure 1, can be achieved in 2 steps as per the disconnection approach. In step 1, you can see here the carbon bromine bond is a polar bond. Carbon is slightly delta positive, bromide is slightly delta negative. That bond of 1,4 dibromobutane is polar, and so lone pair of ammonia can attack the positively charged carbon, which is slightly positive, delta positive. This lead to the formation of a bromide ion, which removes a proton to give 4-bromobutane 1 amine, that is structure 4, and HBr. In step 2, the compound 4, that is 4-bromobutane 1 amine, undergo cyclization via an intermolecular nucleophilic displacement to give our target molecule, that is pyrrolidine structure 1. Well, another example of five-membered heterocyclic saturated compound is a synthesis of 2,2-dimethyl tetrahydrofuran. The design of the synthetic step of 2,2-di methyl tetrahydrofuran, that is structure 5, can be explained by the disconnection approach. Here you can see that after the oxygen on unsubstituted carbon, between unsubstituted carbon and oxygen, Wiggly line is placed, that is CO disconnection. This In this retrosynthetic analysis of this 2,2-dimethyl tetrahydrofuran shows that it can be synthesized by 5-chloro-2-methyl pent-2-ol, that is structure 6. This is achieved by the one bond carbon oxygen disconnection. After the retrosynthetic analysis, then the synthesis of 2,2-dimethyl tetrahydrofuran, that is structure 5, can be achieved by intramolecular Williamson ether synthesis. The synthesis is achieved in two steps. In step 1, sodium hydroxide is a strong base, so it abstracts acidic proton of hydroxyl group, forming alkoxide ion, that is structure 7. And in step 2, oxygen containing negative charge attacks carbon of carbon chloride polar bond, that is in which carbon is slightly delta positive while chloride is slightly delta negative. This partial positive charge leading to cyclization of compound 7 and elimination of metal halide. Another important retrosynthetic analysis of a five-membered saturated heterocyclic compound includes the synthesis of pyrrolizidine. Pyrrolizidine, that is structure 9, is a heterocyclic organic compound and is the central chemical structure of variety of alkaloids found in plants and are used in various traditional medicinal system like Ayurveda. To understand the synthesis of this compound, retrosynthetic analysis is very useful. Here you can see the in this retrosynthetic analysis, applying disconnection approach to the compound 9, we can see that the carbon adjacent to the nitrogen undergoes the functional group interconversion, that is FGI, to develop aldehyde group on both the ends. As discussed in the previous slide, you can see here in this structure 9, pyrrolizidine, uh, after the nitrogen in the first ring between nitrogen and carbon wiggly line is placed, so it will going to give a ring opening over here. Then after the another disc CN disconnection is shown over here in structure 10, will going to give you a cyclic structure, that is amino derivative, diketone derivative, dialdehyde derivative as a structure 11. Well, after the disconnection, let's see the synthesis. The synthesis of pyrrolizidine, that is structure 9, involves the concept of reductive amination, condensation of the secondary amines, that is of structure 10, with an aldehyde or a ketone gives an iminium salt, which on reduction with NaBH3CN gives a tertiary amine. The synthesis is carried out in four steps. Step 1, the lone pair of the amine group attacks the carbonyl carbon to form iminium salt, that is structure 12. The iminium salt formed is reduced with NaBH3CN to give uh, secondary amine. NaBH3CN reduce iminium ion selectively in presence of carbonyl group. The lone pair of secondary amine attacks the carbonyl carbon to form iminium salt, and in step 4 the iminium salt formed is reduced with NaBH3CN to give a tertiary amine. Well, here the synthesis of pyroxylidine structure 9 is given. You can see here the starting material treated with acid hydrolysis will going to give one cyclization between this carbon and nitrogen. Will going to get this cyclization, then it is followed treated with NaBH3CN. We will going to get this amine, and then after on acid hydrolysis again we're going to get structure 13, which further treated with NaBH3CN will going to get our target molecule. Yeah, the synthesis of six-membered heterocyclic compound and its example is given. The retrosynthetic analysis of structure 72 is given. You can see carbon nitrogen di-X double disconnection is shown, and then there is two wiggly line on the alkene as will give to dialdol, and it gives the starting material, that is acetone. So the same method work here well with the six-member ring. So we shall look at a few instructive examples over here. A drastic demonstration of the advantages of intramolecular reactions come in the synthesis of tetramethyl piperidone, that is here the structure 72, that is the tetramethyl piperidone. A removal of the nitrogen with conjugate addition of ammonia to the Dinon, that is 73, opens the possibility of a double aldol disconnection to reveal the three molecule of acetone here. In the synthesis, you can see the treatment of acetone with ammonia and the mild dehydrating agent calcium chloride at room temperature gives the piperidone 72 in one step reaction. We can presume that the acetone can dimerize and trimerize, but the incipient polymerization is nipped in the bud by the capture of one or more of these intermediates by ammonia and the formation of the uh, possible stable six-membered heterocyclic ring, that is piperidone 72 structure is going to be obtained. The yield is 48% since the PUA, but the excess acetone is recovered in the isolation, and the yield is converted to up to 70%. If that is taken into account, this is going to be very cheap and useful uh, process to obtain the piperidone 72. Well, this is enough from my end. Thank you for paying attention to this video lecture. Keep asking question. As you know, asking question is a beautiful way to gain knowledge. Thank you.